So, welcome. I'm here to talk about missing and potentially future C++ range concepts. So, I work at ThinkCell, and despite our logo appearing on all the videos, we're not actually the company that does the video processing. We just really like C++, so we sponsor all the conferences. We are based here in Berlin. We sell a plugin for Microsoft PowerPoint that makes it a lot easier to create slides. So like all the management consultants, they all use our plugin. We have like automatic layout. We've got more chart types. We are really deeply integrated into Microsoft Office because we hack ourselves into it. So we have like a team of reverse engineers, and then we do like detouring of some of the functions. So it's all done in C++. We're really passionate about C++, and we are hiring, but this slide doesn't have the hiring link. So, but we are. Talk to me later. So this talk is based on some of the experience I have maintaining our ThinkCell standard array. So it's heavily built around ranges, but it predates both stud ranges and range v3. Like range v3, it is an evolution from boost ranges. And similar to Flux, it's implemented in terms of cursors. If you know what that means, good. If you don't, not important for this talk. Because unlike Flux, the cursors are an implementation detail. Some of it is public, and I've given a talk that talks about some of the nice features. So this talk is about missing range concepts that we have implemented in the ThinkCell standard library and should be standardized, some of them. My implementation concerns were C++ 23 as compiled by MSVC, so not quite C++ 23. Oh. Okay. But for convenience, I will present them assuming full C++ 23 and sometimes C++ 26 features. Also, for easy understanding, I will pretend everything is in namespace stud ranges and not TC ranges. So when we have an equivalent, just so you know what that means, and I will use the stud names and not our names. And there's no promise that any of this actually makes it into the standard array. I happen to chair the study group that is in charge of stud ranges at the C++ standardization committee, but I don't plan on proposing all of them, and then people can also reject stuff. So like no promises that this actually ends up in the library. So this is a shortened talk of a 90-minute version I gave at C++ now. So I've only brought 2 problems if you watch the full version by watching this video. But anyway, so 2 problems are optimizations about better performance, and then the second one is a bit of metaprogramming for compile time magic. So for conventions, I will use stdv to refer to stud views and stdr to refer to stud ranges, and potentially future extensions I will just use std2 and std. So let's begin with the first problem. Let's suppose we have a file and we want to read it, but we want to normalize all tab characters to 4 spaces. Using stud ranges, the basic thing is pretty straightforward. So we have a read file function that returns a range over all the characters. Then we transform each character. If it's a tab character, we replace it with 4 spaces. Otherwise, we keep it unchanged. And due to the small string optimization, this doesn't actually allocate anything. And now we've got a range of strings, but we want a range of characters, so we join it and then convert that to a stud string. And now the read file function is simply something that takes a file path and returns an input range over all the characters. So it's like lazily reads characters. And the way you want to do that is like you have some iterators. The iterators maintain state in a buffer. And when you dereference an iterator, you just get whatever is currently at the buffer. But if you increment it and you reach the end of the buffer, you call read more, which then resets the iterators to the beginning of the buffer after reading the entire buffer. So we don't want to call read on like every single increment, every single character. We want to read like big buffers at a time and then just provide that buffer incrementally and just keep reading it when we reach the end. Now, for the first problem, let's introduce something that we at ThinkCell call generators. So this is the code we've written using iterators. We read the file, we transform it, and then we join the thing. But this is how you write it imperatively. So you have a loop, and you keep calling read more. This gives you like a span over the parts of the buffer that were filled. If this is entirely empty, then we've reached the end of the file and we're done. Otherwise, we iterate over each character in the buffer. Everything so far is done by read file, so to speak. And then we transform each buffer and iterate over the translated one, and then we do something with it. Right? So if we know what we want to do with the characters, we would just put it in the little 3 dots in the middle instead of using stud ranges. Now, The upside of the imperative code is that the iterator is a state machine. So when you've got an iterator, let's begin with the outside. So we've got the join. A join iterator has an outer and an inner one. So the inner one is, in this case, an iterator over the string, and the outer one is an iterator over the current transform part where we got the string from. The transform iterator doesn't introduce any additional state we care about, like it has a function object, but let's ignore that. Just the iterator to the base, and then our base iterators has the 2 pointers. And now we're having 2 important functions. The first one is dereference. Dereferencing a join just dereferences whatever we currently at. Dereferencing a transform just dereferences the base and then passes that to the transformation function. This gives us a string in this case. And read file again just dereferences what we currently have. Increment is a bit more complicated, so join increments the inner operator, and if that one reaches the end of the current range we're joining over, so it reaches the end of star outer, because star outer is the current range, and so we reach its end, then we need to go to the next one, and the immediately next one might be empty, so we have a loop to skip over all the empty ones until we reach the next non-empty one, in which case we reset inner to the beginning of that one. And presumably, you need to at some point check whether you reach the end of the outer one, but I've omitted that here. Now, transform increment just forwards. And for read file, it's actually very similar to join. So we increment the buffer, check whether the end, and then read more to fill the bag. Now, the imperative code was just a bunch of nested loops. Whereas the iterators had the state machine where we split the loop into a read step, an advanced step, and then each step can arbitrarily advance deeply nested submachines. Right? So we have inherent overhead when using iterators compared to the nested loops. And especially problematic are iterators like join. Like join is logically 2 nested loops. We loop over all ranges in the outer one, and then for each range we iterate over itself because it's another range. Right? So we have 2 nested loops. Concat is n ranges in sequence, and that is logically n loops in sequence. Yet the state machine is particularly complicated because we have a variant of all the iterators, and then we increment the current one. And if that one is the end, then we change the variant to go to the beginning of the next one. Right? It's just n loops in sequence if we write it imperatively. Transform or filter is logically 1 loop with an if, but the filter increment has to call the transform to find the next one that matches. And then when we dereference, we call the transform again to get the current value because we don't store it anywhere. So there's some overhead there. Now, why do we need the state machines, right? We need the state machines because we're using a pull model. The range consumer is in full control, right? This means that we have a range, we can call begin, then we have some kind of iterator, and we start using it. We want to skip that, use the value again, skip forward 2, use the value again, and then we're done and we no longer do anything. We're in full control of what we want to do. However, often the state machine model is completely unnecessary, right? Because what we're having is a range, and then we have a loop that goes over the entire range. Then the user does not need control, right? We just want all the values of the range. And so every time we use a range-based for loop, this range is represented by a potentially complex state machine, and then this state machine is repeatedly advanced until we are complete, right? That's wasteful. We didn't need the state machine to begin with if we just want to get all the values, right? So it's better, in this particular case, to use a push model. There the range producer is in control. So the range pushes the values onto the consumer using a sync function object, and then the consumer processes them one at a time. And so ideally, we could customize the entire loop. Barry Refsand and I had a language paper a couple of years ago. This was unfortunately rejected due to complexity of rewriting the loop. Point of note that since then Go has implemented that in their language, so take that what you will. And Barry also managed to implement that entirely using token injection in an experimental compiler with just really horrible syntax. But it's C++. So at ThinkCell we can't change the language and we can't use reflection yet. So instead we have a library solution for that. We call it differently, but for the purpose of this talk, let's call it for each while. So for each while iterates over range and calls the sync for each element as long as the sync returns true. And this allows us to model loops with break in them. And so it has a default implementation. The default implementation just takes an arbitrary input range and falls back to the range-based for loop, passes each value to the sync, and returns false. It returns false if the sync returns false, and that way we can propagate the cancellation out if we nest multiple for each whiles. However, we can also customize it. For example, for transform view, we can customize it to just call for each while on the base loop and then push the transformation into the sink. Right? So we only do the transformation the second we pass the value onto the sink. Right? So we wrap the sink instead of transforming the range. For join, we can actually write the two nested loops. Right? If join is an inner loop and an outer loop, and we can express it. So we call for each while on the outer one, and then each element is a range, so we call for each while again and pass the sink. And similarly, for the read file loop, we can sort of write the imperative code we've seen before. So we've got the while true loop, where we repeatedly call read more, and then pass that entire buffer to the inner loop, where we then call that to the sink. And again, we need to like handle short circuiting. This is why the for each while returns whether we stopped. And now that we have for each while, we can use it in all the algorithm implementation that are essentially loops. So like for each, copy, min, max, count, they can all be implemented in terms of for each while instead of iterators, right? Similarly, because it can like exit early, we can also use it in the short circuiting loop. So like all of, any of, none of, equal, or contains. Now, crucially, the difference is, if we have a for each while over this complicated range expression and a sink, after one level of inlining, we implement the for each while specialization for join, which calls on the base and then gets the string and then passes the string to the inner one. If we inline again, so the string is just an iterator, so we get the default implementation that uses the range-based for loop, because we can't really do any better than that. If we inline again, we inline the for each while of the transform, which just moves in the transformation into the middle of the loop. And now if we inline one final time, we have a read file, which gets its implementation, and then we do this. And as you'll notice, just by repeatedly inlining, we ended up with the imperative code. We don't have a complex iterator state machine that's like opaque for the optimizer to see. We just directly end up with the imperative code just by doing inlining repeatedly. And optimizers are really, really good at the inlining. Now you might ask yourself, why not use coroutines? Right? Like std generator allows us to do exactly that. Right? You just write the imperative code and they put the co-yield in the middle. However, coroutines are fundamentally state machine. It's just that the compiler generates them instead of you. Right? It's still the pull model and not push. But in addition, we also have additional overhead. They do heap allocation. Right? And so they're not really feasible to solve this problem. We really need better optimizations for std generator. So we sort of have like the natural syntax with the bad performance in like multiple cases. So like for each while is sort of the equivalent to co-yield. And if you're familiar with senders receivers, they are like a more optimal co-await. It's really unfortunate that we have to resort to the library to make the language faster. But you know, what can you do? Now this for each while pattern is really powerful because just by inlining, we can completely avoid the iterator overhead and get measurably faster code. But of course, it's not quite as simple as just adding a customization point and then using it everywhere and then people are happy. Like for example, we can't implement reverse view, right? Because it needs to iterate in reverse and we can only iterate forward. So we can't customize it unless we also have a for each while reversed, and then for each while for reverse would delegate to for each while reversed. But then we also need to implement like each customization point twice. We actually do that at ThinkCell by having our like for each while customization point takes a Boolean whether it goes forward or backward, and then we implement everything twice, but it's kind of annoying and like, is it really worth it? Fundamentally, view zip iterates over multiple ones in lockstep. And you can't really do that with for each while. So you can only call for each while on one range, and then you have to use iterators for all the other ones. So like one range drives the loop, and then the iterators are used for the other ones. And this means that if you have a for each while of a zip of like a concat and a std string, you don't want to use the for each while implementation for the std string and then fall back to the iterators for the concat, because that's slow. You want to use the for each while for the concat and use the iterators for the std string, but then you need some sort of trait to figure out how, like which one has like the worst iterator performance compared to for each while, and then you pick that one. And we have something like that, but it's like not ideal. Then we fundamentally cannot support find. Like find gives you an iterator, and we can't implement it in terms of for each while because we don't have the iterator. Now we could imagine a for each iterator while, which does not give us the values. Instead, it gives us the iterators. And then we can do something like that, but that means that we still need to have iterators. And in a concat, that involves constructing a variant, and then we might lose any performance gains. And then there's this concept of generators. So in principle, like we can make anything rangeable with the simple algorithms by just writing for each while without even having to provide iterators. And so do we want to adopt that to the standard? Do we want like sort of ranges that don't have iterators? They just can be looped over, right? And so you can use the simple algorithms, but you can't use the algorithms that provide iterators. And I think so we do, but for the standard library, I'm not so sure. And of course, the big problem, all of those optimizations completely ignore the range-based for loop, right? So whenever you use the range-based for loop, you don't get the optimization because this one is defined to fall back to iterators. So I think so we actually ban the range-based for loop. We have to use for each because that's significantly faster than the range-based for loop as soon as the ranges are non-trivial. Now, the power of for each while and generators doesn't really stop there. We can also look at chunked ranges. So if we have a range and then we want to convert that to a string like we do in our initial examples, this is the implementation of toString. So whenever possible, we reserve it. So when it's an approximately sized range, a new concept in C++36, it provides a reserve hint function that gives sort of like an upper bound that's reasonable for the range, and then we use that. And if the range is sized, this falls down to size, and then reserve hint is just size. If it's a forward range, we can loop over it once to compute the size, use that. But if it's an input range, then we can't really do that because if we looped over it once, now we know the size, but we can't loop over it again, so that was kind of pointless. And so in this case, we will have like repeatedly regrowing when we do the copy with the backend sorter. Now, of course, there's one optimization that you could do if you have a contiguous range. Then you can just use append on the string member function, which presumably then falls back to memcopy of the contiguous memory and is more efficient. Right? But not all ranges are contiguous, but many have contiguous chunks. So contiguous ranges are vectors, arrays, strings, and spans. They're nice, they can fall back to memcopy, all good. But like a deck is like a range of like contiguous chunks, right? And so it would be nice if we could somehow use memcopy for the contiguous parts, but still also allow that, because you can't memcopy the entire deck, you can only copy chunks of it, right? Similarly, if you concate two vectors, that's clearly two contiguous parts, so you want some way to like make that possible, right? Also, if you have a range of spans and you join it, same deal. You now have many contiguous chunks, right? And our read file is exactly that. Like it repeatedly gives you the same span, right? So it's a range with contiguous chunks. And we somehow want to make sure that we can fall back to the optimized solution using memcopy. So the problem is, some ranges have this natural segmentation into chunks, and we want to express this chunking to take advantage of that in our algorithm implementation. And now the good news is, we already did that. We already completely expressed this chunking, namely when we specialized for each while. So our for each while says that we're having an outer loop, and then we're having an inner loop, right? And this is a natural chunking. Right? Similar to the read file, in the inner thing, it keeps passing the same span to the for each while buffer. So actually, our contiguous chunks of slides. Actually, our for each while implementation has a second customization point. So the highest level of priority, if you call for each while, it checks whether the sync provides a chunk method that accepts this entire range. Then it falls back to the specialization for each range, and only then does it fall back to the iterators. And it's really crucial that the sync gets to customize first and then the range, because the sync might know better how to handle a particular type of range than how the range knows how to better express its loop, right? Because in the case of string appending, we could imagine a string appender sync, which is just callable with a single char and calls pushback, but it has a chunk member function that takes a contiguous range and then it calls append. And now, whenever we give it a contiguous range in for each while, this entire for each while will fall back to chunk and call append instead of repeatedly calling pushback. So we should really implement toString instead of having copy with the back inserter. We should have a for each while with a string appender sync. Because then, if we do a range of spans that we join, after one level of inlining, we get the join implementation of for each while, because the sync doesn't provide anything for join. Like join isn't a contiguous range. But now in the inner loop, we're calling for each while on x, and x is a span, which is a contiguous range, and the sync knows how to accept contiguous ranges. So this one calls chunk, right? So now we did what we want. Each span calls append, which boils down to memcopy, and we iterate over each of the spans and keep calling append, right? And we got this entirely for free. right? We didn't need to do anything else. Just by providing for each while, we get this natural segmentation, which we can then take advantage of. And so sinks are the superior output iterators, right? Like output iterators are kind of clunky. They have this operator plus plus and the operator star overloads, and they have no ability to receive chunks. A sink is just a function object that takes a single value, and optionally, you can opt in to receive particular chunks. And so the standard library should really support the sink interface in addition to the output interface and only use that for compatibility. So imagine something like we copy a range and then we use append2, which creates a sink that parses the container, and internally it handles contiguous chunks appropriately and falls down to the most efficient implementation, right? Like you can imagine that if you have a linked list, like that you do something with copy, then the append2 for linked list can like take ownership over the list and just add it in line without having to do any copying, right? And these sort of things. They just naturally fall out of the model. Now, it is then also crucial that the pipelines express this chunking. So if you're just calling read file, we're getting a range with big contiguous chunks. Like each of the spans is a contiguous chunk. Then when we transform it into a range of strings, that's no longer contiguous, that's fine. But when we join it, we have a range with like tiny contiguous chunks, right? Like each of the std string is like one contiguous chunk, but it's like either 1 or 4 characters. So we don't really get a lot of the chunking benefits. It's much better if we rewrite this pipeline using something like this. So we read the file, and then we split it at the tabs, and then we join that with the like 4 spaces in between each tab. That way, each of the resulting things is either like the contiguous span between 2 chunks, or like a tiny chunk with 4 spaces. And so we keep calling like the contiguous append on the big parts while forwarding the tiny ones, right? But if the tiny chunks are rare, that's fine, right? Like we get the chunks, right? Like if we don't have any tabs, we haven't split it and we kept it just accumulating contiguously. So that's really nice. And making a chunk join with is also not that hard. So this is a for each while implementation for join. We just need to either pass in the separator or the actual element to the sink, and then the sink gets to customize how it's going to do that. So that's not very hard. It's just handling the first one is the annoyance, but you know. Now, unfortunately, this doesn't work for annoying technical reasons. Namely, that split requires a forward range and the read file is an input range. And there is a lazy split, but the lazy split one does not keep the contiguous chunks property, because by design it has to like cache stuff and then we lose it, right? So this fundamentally doesn't work. However, in this particular case, we don't really need to have like one range that contains all the chunks. We're fine with sort of treating each chunk one at a time as we get them. So instead of just having read file, we should also have read file buffers. And read file buffers gives us a range of spans. And then read file is just read file buffers and we join them all together. And this also neatly expresses the fact that like the for each while implementation of read file was very similar to the ones for join. It's just the thing in the middle was slightly different, and this expresses that. So for each read file is now implemented in terms of join and the underlying primitives that gives you the range of spans. And then we can implement a read file normalized in terms of read file buffers. So read file buffers, we get a range of buffers, and for each buffer, we want to do the split and the join with. Inside each buffer, we can do that because we have a contiguous chunk, right? Like read file was an input range, but read file buffers is an input range of spans which are contiguous. So as soon as we then do it one chunk at a time, we have contiguous ranges, and we can use all the powerful ranges. Now the end result again is like a range of the contiguous chunks but correctly normalized, so we join them and put them in a std string. Right? And this is a better approach on dealing with this problem because we now keep the contiguous chunk property in a way where it actually compiles. And in fact, things are because we have ranges that don't provide iterators and only provide contiguous chunks, that only provide for each while, we can actually implement read file buffers in terms of the read file implementation. Because all we need to do is provide for each while, so it gets it calls for each while on the base with a sink that extracts each chunk and passes the chunk as a single value to the sink, right? Of course, we can't do iterators on top of that, but we can provide for each while that does buffers at a time. And so that is still nice. And so sort of with like this implementation, this sort of undoes the join in the very generic way while keeping all the performance. Okay, now for the second problem. Now, a colleague was working on some way to describe an SQL schema in a compile time DSL, and then he wants to create SQL statements to create the table. Right, so something like this. So he says like people is a table, that's the name of the table, it has 2 columns, and then I want to have the create statement, and I want to get at compile time a string to create this table. Now, 2 things before we get started. I need to talk about the difference between compile time and compile time. So the fundamental limitation in C++ is that within a const-eval function, the arguments are const-eval. So the first line is okay. We're having a string literal, we're passing it to const x plus trillion, which gives us a compile time value. We can use it in a context where we expect a compile time value, everything is good. However, the second one isn't okay because we're having a const-eval function. And even though this function is only ever called at compile time, within the body, string isn't a compile time constant. So we can't use it in place of a compile time constant. Right? And so to work around this, we need to embed the relevant information into the type of the argument, because the type of the argument is known at compile time. And so instead of passing a string, we need to pass some type that encodes that string value, and then we can get the size at compile time, and it is truly at compile time. It's a bit silly because we are at compile time, so it should just work. But that would mean that the compile time interpreter needs to know how to instantiate templates as it evaluates a compile time function. And that wouldn't make it, like, compile time is already slow, and that would make context by evaluation even slower if it then has to start and instantiating templates, and then we're just having a dynamically typed language in the middle of all, like, at compile time. It would be weird. So I get why it's there, it's just annoying, right? So I'm going to call this early compile time versus late compile time. The value of the string parameter, if it's just passed a parameter, is only known as late compile time, so we can't use it to instantiate stuff within the body. Only when we then return it and in the outside scope can we actually do it, whereas the type would be early compile time. So this is the first thing. The second thing is, what is this? The size of the string literal ABC. It's 4 because of the null terminator, right? String literals arrays. Arrays have a null terminator, size sees an array, it gives you 4 and not 3. So we need to have string literals in a custom type, just to make the range algorithms work. At ThinkCell, we actually redefine begin and end for string literals, so it just removes the null terminator, but I wouldn't recommend actually doing that if you in your own code unless you control the entire iterator pipeline. So both of those solutions, early compile time versus late compile time, so we need to encode the string literal in the type system if we want to do stuff with it, and we need to get the type. Those ones are both fixed by what we call a literal range. So literal range is just a bunch of t's, but we put the t's in the type. So now we have them available in early compile time and can use them whenever we want. And then it has a begin and end that like synthesizes a static array somewhere at compile time, and so we can start iterating of it. And then we have a TC literal, we call it TC for ThinkCell because it's actually a global scope. And that one just takes the string and wraps it in a literal range. And now we solved both of the problems. So the size of ABC underscore TC is 3 because it's a range of 3 characters. And the size of a literal range parameters a compile time expression, which is what we'll need. So let's actually start implementing this create function. So this is a first attempt. So we've got an object, it has a type and it has a name. And now we want to create a SQL statement. So this is what we want to write. We want to write create is create plus the type plus the space plus the name. And like the wish list is ideally, like there are many ways to solve this metaprogramming problem, but what we want is we just want to use the range algorithms, right? So we just want to use concat to concatenate the strings, convert that to a std array, put that array in static storage, and then return a string view of that array, right? This is the code that we want to write. Now, the first thing that we need to implement for that is toStd array, which has a really obvious problem. It needs to know the size early, right? It gets a range, and then we need to instantiate a std array with the size of the range. Unfortunately, the range is a parameter, which is not const x inside the body, so this one doesn't work. Except it does, kind of. Thanks to my favorite C++23 paper. This paper just makes it work. So we can write code like concat ABC, an array of 3 characters, get a range in a local variable, and call size of that range and statically know 6. Because this paper changed something. As long as you don't access the runtime values, you can use local objects in const x by code. And when we call std size, we're calling std size on concat view. And so std size on concat view just calls std size on all of the members in the range. And each of those members is either an array whose size is statically known, or a literal range whose size is statically known. So at no point does it actually access any dynamic data. Right? So the code just compiles and works because it doesn't need any dynamic values. We can just use a local variable at compile time as long as we don't actually access any of its members. Right? And this is like magical, but it's like really, really useful. It's like so cool. So now we just need to teach the standard library of that. So we can imagine a new concept of compile time sized ranges. So that's a range that is sized, and we can use the size at compile time. So calling std size doesn't actually read any members, right? So like a std vector wouldn't be compile time sized, but a std array would be. And the std concat view of an array also would be. Right? And like, let's bike chat the name some other time. And then we can write a function const by size, which takes the range and actually gets us the size. Now, unfortunately, declval like this doesn't work because it's not const expa. There are like workarounds you can do like this. It's not important. I just put it there for completeness. I plan on just making it work because right now we have to do this thing. I'm a bit short on time, so I'm just going to skip this part, just whatever. We can make it work. Right? And I think so we also made it work before C++23 because MSPC hasn't implemented the paper that, and that one's more annoying. We have to like specialize the trait. It's doable. I've written a blog post about it. Just annoying. The C++23 model is really nice. Now with that means that std array just looks something like this. So we just create the container. We require that it's compile time size, so we can call std range size to instantiate the size of the array. Then we copy it over. Except this one requires like default initialization, so you just use this instead, where you like do a fault expression and then a braced initializer. Not important. We can make it work. And with that, this code just works. Right? We're done. Right? We can create string literals using the range algorithms at compile time. Everything works. Now, unfortunately, it wasn't that simple. So first of all, we're using a concat with instead of concat, which just puts in the separator in between. That's not a problem. It just works. This is concat with. It just takes a bunch of ranges and the separator and just does a fault of prepending the separator over all ranges except the first ones, and then concatenates that. And concat optimizes nested concat, so there's no problem there. Unfortunately, however, the actual object thing also had qualifiers. So we also want to put in qualifiers. And the qualifiers can be empty, so instead of concat with, we need to filter it out if they're empty. So we have a function concat non-empty with. And when I started, this was the implementation of concat non-empty with. So we take the separator and all the ranges, and we first to convert the pack into a range. That way we can filter out the empty ones and then join it back with the separator. Right? So we turn the parameter back into a range, we filter out the empty ones, and then we join the remaining ones. And this didn't work at compile time. Like it didn't produce a compile time sized range. So because the join with wasn't compile time sized, and like because the filter thing isn't compile time sized, because how would it know when to filter stuff? Right? It just fundamentally didn't work. So I just said, okay, no problem. I can specialize it. If all the ranges are compile time sized, we just use this implementation. We can filter out the parameter pack at compile time to filter out the empty ranges. Then we have the empty ranges, and then we just use concat with. Right? It works. It's just a bit of ugly metaprogramming. So I submitted it for review, and my boss was like, yeah, no, just, this is nicer. Can you just not make this one work? And that were the next couple months of my life, which I'm going to present to you now in 25 minutes. So let's begin with make range. This was make range. It takes a bunch of ranges, and it puts them in an array, by like using the comment type, and then puts them all in a range. Now the first problem is, each element of make range has the same type. Because the range is homogeneous, right? All elements have the same type. Which means that if we create our fancy TC literal ranges, the comment type would be a std span. And then we've lost all the size information. Right? Because it's no longer encoded in the type system. It's a std span, it stores it at runtime, and this is no longer a constant expression. So we need to make sure that we don't put them in a comment type, right? So we need to change make range to use a tuple. Now, of course, a tuple isn't a range. For the very simple reason that if you do this, like what is the type of X? Right? Like it's a variant of all the values, right? Because it's a dynamic index into the tuple, so we don't know the type, so it's a variant. But this adds overhead, right? We really don't want to add iterators to tuple. But what we can do is we can give it a for each while. So we can give it a for each while that just invokes the sink for each of the values. And this doesn't have any overhead because we just pass all the values to the sink. Now, of course, it's different from a range because the sink is instantiated with different types, right? And this is the difference between a homogeneous range or a heterogeneous generator. So homogeneous ranges has begin end and optionally for each while, and one common stud range value type. With heterogeneous generator, you only have for each while. You can't implement iterators. And instead of a single type, you have a variadic type list. We call it the generator output. With ranges, you can use all iterator-based algorithms. Potentially, you get the optimization. Whereas with the generators, you can only use the for each while-based algorithm, right? Homogeneous ranges, you can use the range-based for loop, whereas you need a for each while with a generic lambda for heterogeneous generators, right? But every homogeneous range is a heterogeneous generator, but not vice versa. Right? And so we can make tuple a heterogeneous generator, right? Implement for each while, have a for loop over tuple. Or we can have a for loop over an index sequence, right? Which just gives out each value as a compile time constant, and then we can process it compile time. We can also use like a type list with an algorithm, right? We just get all the types. Right? Matt Goldball gave a keynote at ACCU where he implemented emulators. And what he wanted to do is he wanted to compile each opcode of a Z80 assembly instruction into a function that executes it. And he wrote this code on a slide and says, okay, so we have all the opcodes between 0 and 256, and I want to transform each opcode into the instruction. So we take the opcode, we decode it, then we have the instruction, then we compile the instruction into a function pointer, and then we turn that as a std array. And then we have the list of all the handlers to compile the opcodes. And he said, of course, this one isn't valid code because you can't put the const x bar with the opcode, and you also can't put that in the std array, even though I set the size as 256. Like, it just doesn't work. But with everything I've shown you, this one works. Right? So we start by using an integer sequence instead of iota, because that one is compile time sized. Then we're getting each byte as a compile time value, so we can actually decode it at compile time, get our instructions, compile it into a function pointer, and collect it all into a std array. Right? This is just really straightforward metaprogramming by just using the ranges algorithm. Right? He also gave a second example, which would look something like this. Now we can also like extend further. Now that we know that, for example, when we filter, we get the different types. We can start filtering based on the type. So if we know that, for example, the predicate we're filtering on is compile time known and doesn't depend on the actual runtime value, we can use an if const x bar instead of a plain if, and then we only instantiate the sink with types that are statically known to satisfy the predicate. And that means we can turn a tuple, we can keep all the ints and convert that into a vector int. And this code just compiles, right? Because at no point do we actually try to like push back a string literal into the vector. It's entirely filtered out at compile time. Anyways. So at this point we're here. We're calling make range and we're getting a compile time sized range with compile time sized elements. Next up, filter. So obviously, as soon as we filter it, we're no longer compile time sized because we strip elements, so we don't lose the site information. However, we could give it a size. Like for starters, filter view isn't even sized to begin with, right? Because this would be an implementation of size and this has a loop. Right? So size has to be 01, this isn't allowed. However, if the range is const x bar sized range, well, it's technically 01, because it's a compile time size constant. Right? Which is technically true, but not in the spirit of the runtime complexity. However, we could argue that if it's a compile time sized ranges, and the predicate only depends on the types, that's what the second option says, then it's 01, and it's just an 01 of like compile time known true, false, true, false, true, false that we're summing. Right? So it's 01 and hopefully optimized. However, I need to implement it with the const x bar size specialization, and I can't call countelf because I don't have any values to call countelf. And so I couldn't do it directly, and this was good because I was also missing a case. So the condition wasn't enough to get a compile time known size. Because consider these two ranges. So we've got a tuple of ints and a tuple of doubles. Both of those are compile time sized, so the static assertions pass. And then we can imagine a conditional range, which based on a condition either iterates over gen 1 or gen 2. And this one is also compile time sized, because the condition is runtime, but in either case, we're having a range of the same size. So the size is still 3. But now if you filter out all the ints, this cannot be a constant expression, the size of the resulting thing. Because the size is either 0 or 3, depending on which value of getchar we got, but that's the runtime value. So we obviously lost compile time information. So filter can only be a compile time size if the range has a compile time size, the underlying one. The predicate only depends on the types of the elements. And we know the type of each element that we will end up iterating over at compile time. And the last condition wasn't true for the conditional one. And so we call the range with, and for that we need to know the types, the actual types. We need to know what is the 5th type of the value, right? And so we introduce tuple generators. Those are generators, so they implement for each while. They're compile time sized, so we know the size at compile time. And we also provide the tuple interface. And then we can keep composing them. Like most views of tuple-like generators are themselves tuple-like generators. Right? And this is sort of the table we're at. We've got the generators, which only support for each while. We've got the tuple generators, which support the upcoming template for, where you can write a for loop that just expands over all the elements. And we've got the regular ranges, where you can use the range-based for loop. And with tuple generators, we can actually implement filter view, the size function. So if you have a tuple generator and the predicate is only compile time sized, then all we need to do is we need to count all the sizes of the things that match the predicate. But this entire count happens at compile time. So this function guarantees to return like a compile time known value, right? We're having a compile time sized thing. We do it at O1 because we do the loop at compile time, which I think is O1. And then we can also make it tuple-like by just mapping the index to the base index, accounting for skipped elements. We can compute a lookup table at compile time, and now we've got a filter view that is tuple-like. Now that means we're now having a compile time sized range with compile time sized elements, because we know the compile time size of the entire range, because filter has now compile time size, and we know the compile time size of each element because we started out with compile time sized elements. Last thing, join with. Join with is no longer compile time sized. So this was the size implementation of join before I did my changes. So the standard library join never provides a size because it would need to sum all the sizes of all the subranges, which it obviously can't do in O1. However, if we know that we're having a sized range and all output types have the same context per size, then it's just a multiplication, right, of the base range plus this, right? Like if you're joining a range of tuples of like a range of arrays of size 3, the resulting thing will be whatever is the range of the outer one times 3, right? So we know the compile time sized. But this isn't the case here, because here we're having like each of the elements we're joining can have different sizes. So I need to extend the condition. And we can extend it like this, which is if we're having so either we need all the same size or the base range is a generator. Because if it's a tuple generator, then we can just do, again, a compile time sum of the sizes to get the appropriate size, right? And again, this is a 1 because it's a loop happening at compile time, right? But at this point, I noticed something. Like, I've written this code just a couple days before, right? Like, this is the size of a join view, and this is the size of a concat. This is the for each while implementation of join, and because the concat has a tuple, and we want to like call for each while for each element of the tuple, we just call for each while on the tuple, and then call for each while on each element of the tuple, right? Like, this is the same code. A concat really is just a join of a tuple, right? Like, a concat is literally a join of a tuple, right? We have a parameter pack of ranges, we can turn that into a tuple, and we pass that tuple to join. And then we've got a concat, right? Because we're having a range of ranges and we're joining them, right? And of course, you can like provide various, like you need to then specialize the implementation to account for the different scenarios. So we're having a tuple-based join view that is just concat view. We're having a range-based for loop that corresponds to the traditional join view. And we're having a generator-based join view that doesn't have any iterators and implements for each while. And that means that this code that filters out the empty ranges and then calls concat with, versus the other code that calls make ranges, and then we're filtering stuff, and then we're joining them together. They are the same exact algorithm, right? And I don't mean they're semantically identical. I mean literally, after all the inlining happens, this is the same assembly code, right? We're just doing metaprogramming using the range-based algorithm instead of the weird ugly one, right? Which meant that after I taught the library all of the infrastructure updates that we needed, right? The actual change to make concat with separator work in the use case where I wanted it, like concat non-empty with, was just this. Right? Like I didn't need to touch anything. It's just the range library now does the template metaprogramming for me, and it automatically all falls out, right? And so, yeah, my boss was right. I shouldn't have implemented the metaprogramming. But anyways, I have 15 more minutes. That means I'm going to do the bonus stuff. So, entirely different, unrelated to the rest of the talk. This is some code that finds the smallest Fibonacci number above a given value. So we first start out by getting all the values, all the integers, and then we're transforming each one to the nth Fibonacci number, and then we're finding it. Now let's look at the C++ standard. A range is an iterator and a sentinel that designates the beginning and end of the computation. A range, I, s is empty if I is equal s, otherwise it refers to the elements in the data structure starting with I and up to but not including the elements pointed by the first iterator j, such as j is s. A sentinel, s, is called reachable from an iterator I, if and only if there's a finite sequence of applications of the expression plus plus I that makes I equals s. A finite sequence of applications. Iota is unbounded. We can do it an infinitely number of times, and we will never reach the sentinel. And so, naturally, the sentinel is called unreachable sentinel, because it is never reachable. However, if s is reachable from is denotes a valid range. The result of the application of library functions to invalid ranges is undefined. What this means is, this code is undefined behavior, because we're applying a standard library function to an invalid range. So is this code, because we're applying a standard library function to an invalid range. So is this code, because we're calling .begin a standard library function to an invalid range. So is this code, because we're calling the destructor of iota view to an invalid range. Now, this problem, we realized this problem like earlier in the year at the standardization committee meeting, and we essentially took this poll. The standard library should not provide facilities that only cause undefined behavior. Like, it wasn't quite worded this way, but we decided, yeah. We should actually be able to use iota view. But like, how do we fix it? Now, let's look at the problem space. So we're having two invalid ranges. Subrange, array plus 10 array, right? Like, this isn't a valid range. Like, the begin is the end, and the end is the begin, right? Subrange of vec1 begin, vec2.end. Yeah, this isn't a valid range. You have two different containers there. Then we're having two infinite ranges. Repeat 42 just keeps repeating 42. Iota of an unsigned value just keeps incrementing, wrapping around, and so on. Then we're having ranges where .end says it's unreachable, but like it's not really true. Because if you have an iota of an int, eventually you will have integer overflow, which is undefined behavior, right? And then there is also the trust me bro range, which is a subrange of a pointer and unreachable sentinel. And then like it claims to be infinite, but like memory isn't infinite. So at some point you will just run off the end. And then we have ranges where we truly don't know, like iStream. Like this could be like if the user types forever, this is an infinite range, right? Like is the generator, the coroutine can have an infinite loop, right? And like what even is infinity, right? Like this is clearly an infinite range. But like, is this an infinite range? Right? Like eventually someone who writes that in will probably get bored, right? Is this an infinite range? Right? We say at the end when we roll the 6, what if we're really unlucky? And then we need to distinguish between like infinite usage. So we have a loop on the server, we get an input, we process it, we print it out. Whereas here, in all of those cases, we are having an iota which is infinite, but then we're combining it with something that's finite. And so we will eventually stop iterating. So we only care about a finite prefix of the infinite range. So let's try to fix that by introducing the concept of an infinity sentinel. So an infinity sentinel is, no matter how many times you increment it, you will never have undefined behavior, and you will never reach the end. right? And this maps in those cases, like repeat, 42, iota with an unsigned, potentially the ice stream view, potentially the generator. But those ones aren't covered, right? Like iota with int will have undefined behavior, the pointer will have undefined behavior, and so are the other ones. And so we also need to cover those ones. So let's introduce like unbounded sentinel. So this is like infinite sentinel in that you will never reach the sentinel, but at some point you will encounter undefined behavior, and that is the actual end. It's just, there is an end somewhere, we just don't know it, right? And this covers the iota for int, the signed one, the subrange for pointer with the unreachable sentinel, and potentially is the generator. But it also allows this ones, right? Like array plus 10 array, yeah, well, if you never start incrementing, right, you're fine, right? You only start encounter undefined behavior if you're like increment, right? So vec 1 begin, vec 2 end. There is a finite prefix, all the elements of vec 1, and only when you go past that, you run into a problem, right? And in general, we've now made any range where we can combine an iterator on the sentinel and compare them is now valid, right? Because they're all unbounded. It's just in most of them, you can't really increment 0 times, right? So this is too broad because we still want to prohibit the truly infinite ranges, invalid ranges. So let's say and make it more precise and say, okay, so it's only unbounded if we actually use the type unreachable sentinel. And now this covers iota and the subrange, but it doesn't allow those ones because those ones don't use unreachable sentinel, you just provide the bonk sentinel. But this one also doesn't allow the generator because the generator doesn't use unreachable sentinel. But like, do we care? Like, should the concepts and the standard library be able to differentiate between like a std generator that is truly infinite and a std generator that will have undefined behavior if you go past enough, right? So this is an open problem that we in the committee need to figure out. Now, what about the difference type? After an infinite number of plus plus I minus begin does not fit in pointer diff. For finite usage, this doesn't matter. For infinite usage, maybe. But also, on like 32-bit system, you can have memory that is bigger than 2 gigabytes, and then you can't put this thing in there. So like this is a hole that we already have, and we should probably just, put some wording in that says that the pointer diff t may not be able to represent arbitrarily distances, right? Because it is the status quo. Now, what about cyclic ranges, right? So given our iota view, that starts at 0, and an iterator that starts at 4. What is the distance between? Is it 4? Is it u and max plus 4? Is this 10 times u and max plus 4? Like, we don't know how many turns around we did, right? And so it probably should be defined to be like the smallest difference, but we just need to do some wording to do that. And so if we figure all this out, we will end up with a new sizing hierarchy. So we've got the sized ranges, which are ranges that have a known finite size. We've got infinite ranges that are known to have an infinite size. And if you just have a regular range, it could be any of them, and we don't know statically. But crucially, because we will introduce unbounded ranges, we will just make iota view work, right? Like, I mean, it still works. It's just the standard says you're not allowed to do that technically. And the concept of infinite ranges allows stuff like this. So for example, we will get parallel range algorithms in C++26, but they require sized ranges. And in this case, this means status quo is this code doesn't compile. So this does a binary transform. So it calls the function with one element from each range and then writes the result to out. And it does it in parallel. But this one could be made from because we don't really need the size of the iota because the size of the range is the one that determines it. So we could like relaxen the requirements to make this code compile by saying either both are sized or one is sized and the other one's infinite. We could also optimize take on an infinite range because take has to do the bounds checking. Like if the range is smaller than 10, it has to stop early. But if we know that it's infinite, then we can optimize it and don't need to do the bounds checking. And this is what I originally proposed in a paper. But then it was discovered that actually the entire thing is undefined behavior to begin with, so what's the point? Anyways, so let me jump back to my actual conclusion. So, which of the parts should be included in std ranges? Something like conditional range. I didn't really go much into detail in the shortened version, but it's like a really nice thing. That's like iterate over one range or the other. That's useful in a couple of places. We definitely want the for each while customization point as a hidden optimization as a baseline, right? It's really nice if the range adapter is just implemented and suddenly your copy loop gets faster, right? That's just a nice free performance benefit. Just recompile to a modern standard and your code runs faster, right? Like that's the best thing. Compile times might take longer, but C++. And we also want the sync-based appenders as better output iterators. Right? Like output iterators are really, really primitive. We should really replace them at this point. Compile time sized ranges, definitely, they're useful, and we get them for free. Right? We can just add the 2 for the stood array. It just works. It's really not that hard to implement. Now, the heterogeneous generators, or like also generators in general that only have iterators, are probably not a good fit, because they're like a wild deviation from the existing range concept. Right? Like in the standard library and the C++ ecosystem, a range is something with iterators, and you can use the regular for loop. Right? And then also you have a single value type. It's like using the ones with multiple types requires like some nastiness having to deal with multiple types. Right? This is non-trivial and probably is not a good fit. And we can somewhat emulate it by using the meta info objects from reflection, which are able to represent arbitrary types, but like in like arbitrary like reflections of types and stuff in a heterogeneous type. So instead of having a for each while loop of a range of types, you could have a for each loop regular range best for loop of a container of stored meta info, and this is sort of equivalent. And now, if you want to work on this, there's the hiring link, by the way. So if you want to work on this, highly welcome proposals. Like as I mentioned, I chair the study group that will see range proposals. We have a really small group. It's a really nice way to get started with the committee. We will be able to find all kinds of weird edge cases in your paper, because some of the people are really, really smart. But we are being really nice. It's a lot less intimidating than trying to like add something to the language and then be faced with like 150 people that all have really strong opinions about changing the language, right? Whereas if you like add a view to the ranges library, only a small set of people actually care. So like it doesn't get very emotional. So I really recommend it, and you'll learn so much about the C++ standard library, just because you're like the other day I learned that we will have an optional int const is a thing that we needed to account for in an edge case in the range adapter. It's like, whatever. Anyways, and like I said, I work at ThinkCell and we're hiring. So if you're really passionate about C++ and maybe you like our standard library from what you've seen, come work with me. Thank you.
Hi, thanks for the talk. I think in the bonus section there was a proposal in the part where what if we make it valid to iterate until we hit the undefined behavior?
Yeah.
But there was an example. There was like iterator from one vector and iterator from another. Yeah. Doesn't it hit undefined behavior immediately when we compare the iterators when we iterate over the range?
Oh, that could be true.
Okay.
Yeah.
Yeah. Okay, thanks.
That's a good point. You can't compare arbitrary pointers. I mean, okay, technically, depending on like which kind of allocator you're using, this could be fine because it's like one allocation and then you just have, right? But like, technically it's undefined behavior. And yeah, it's definitely like right now it's undefined behavior because it's an invalid range. So like that wording doesn't even allow the construction of the subrange. But we just need to relax it in a very designated way because of the auto view issue.
Okay, great, thanks.
So the C++ core guidelines say whenever you can use a range-based for loop, will that have to change after what you said?
At ThinkCell we say yes, because our customized for each is faster than the range-based for loop. And so what I envision is that we're going to bring for each while to the C++ standard library helpful in 29. And then we will have implementation experience with that. And then in C++ 32, Barry and I can go back to the group that is in charge of the language and be like, hey, so the library has this nice optimization. And so we need to start having people to not use the range-based for loop, but it's kind of silly. Can we now please have a fixed range-based for loop, right? And that's probably the approach to go. Because we tried fixing the range-based for loop first, and they were like, yeah, this is really complicated, and we don't really care. And so if we give them a reason to care, the compilers might be willing to.
Makes sense.
Yeah, like essentially the idea we proposed is that the compiler turns the body of the range-based for loop into a lambda, and then passes that to the for each while function, right? Yeah. Okay. I'm out of time, but I'm going to be here until the C++ committee meeting starts in 45 minutes. So.